Let's get started. So we're in the home stretch now, just 2 lectures left, and then just review for the test. So today we're doing chapter 12 and 13. Chapter 12 is mostly about quasi-experiments, and then chapter 13 is mainly about what are called factorial experiments. Chapter 12 starts off with something mostly unrelated, which is program evaluation. So I'll briefly do that, and then the rest of the chapter is on, as I say, quasi-experiments. So a program evaluation is what it sounds like. There's some kind of policy or intervention or program, and you want to do some real-world testing to see how effective it is. So the first step, with a number of steps, the first of which is evaluation of need. So this is where you try to see how big of a problem there is before you decide whether or not you want to intervene. So maybe admin at Douglas looks at how well students are doing on tests. So the need evaluation would be, how badly are students doing on tests? Do we need to try something to improve test performance? And let's say, they do the evaluation of need, and it turns out, yes, the students are bombing the tests. There is a need. That would be step 1. Next step would be program theory. So you develop some theory about what intervention will work best before you try it out. So maybe different profs and administrators get together and conjecture that the real problem is study habits, and that the main threat to good study habits is the cell phone, TikTok, all that stuff. And so they decide that the best way to improve study habits is to have some way of reducing cell phone use. So maybe we teach students how to use those lock boxes. Have I mentioned the lock boxes? These are great. These are, you can get them on Amazon for like $50. You put in a set amount of time, lock it, close the thing, and you can't access your phone for X number of hours. So the program we develop is we're going to get students those and teach them how to use them. So the next 3 steps are the evaluation steps. So you do the program, you try it out, and there are 3 things you evaluate: process, outcome, and efficiency. Process is sort of like a manipulation check, but for program evaluation. So in my case, in my example, you check to see, are students actually using the lock boxes? Are they actually putting their phones in the lock boxes? If they are, that would mean the program is working as intended. The next type of evaluation, you want to find out, is that making a difference? So outcome evaluation, in my example, would be, are the students actually doing better on the test as a result of this cell phone intervention?
Okay, can you say the first sentence again, please?
I forget what the sentence was, but an equivalent sentence, is the program having an effect on the outcome, on the desired outcome?
Your original sentence was, is it making a difference?
Sure, well, that works too. I suppose I've never done this, but this is what I have in my textbook. I just have scribbly notes and then kind of go off the cuff. Whenever I lecture, for years has been the way I do it. I do one practice round with, and this is a good general tip for public speaking. With voice memos, I record my practice lecture and I just kind of go off the cuff, and then I just listen to it after. And then you can sort of practice for free, like without effort. You just familiarize yourself with what you said, and then you can like notice issues. Yeah.
For outcome evaluation, are you kind of looking to make sure that the outcome is what you wanted?
You could say it like that, sure.
Well, no, because outcome evaluation and process evaluation seem to be
They're slightly different.
very similar.
They're very similar. So it's similar to the manipulation check idea. So there's some kind of intervention, and there's some kind of outcome. So the outcome you really care about, in my example, is test scores. The intervention that you're doing is the lockbox. So process evaluation has to do with, are people actually doing this? And outcome evaluation is it making a difference? Or you can think of a medical trial, right? Like, now, that would technically be an experiment, but the process evaluation might be, are people taking the damn pills? And then outcome evaluation would be, are they less depressed, smaller tumor size, or what have you? Yep.
There seems to be, so the program theory, is that also figuring out what might be the problem, how to fix it, and also developing the entire program and also implementing it? Because then the next step is already the intervention.
Everything except implementing it, I guess.
Okay.
Yes, everything. Program theory, you're right, kind of is cramming a lot in there.
Alright.
But yeah, everything except implementing. Yeah.
And if we're not talking about implementing, we're just going straight to like, it already happened, let's check.
Yeah, at least the terms you have to memorize. Yeah. Yeah, that's correct. Okay, the final step is efficiency evaluation, which is a kind of cost-benefit analysis. So let's assume that both process evaluation and outcome evaluation are positive. You might then ask, well, how much did this cost? How big was the difference it made? And is it worth it? Given, are we getting enough bang for our buck, as they say? Okay, so that's program evaluation thrown in at the beginning. But as I say, the bulk of the chapter is on quasi-experimental designs. Can someone tell me, what's a synonym for quasi? What does quasi mean?
Sorta.
Yeah, sorta, kinda, almost, but not quite. So a quasi-experiment, and this is a perfectly fine definition, is a sorta, kinda, almost experiment. It has some features in common with an experiment, but it's missing some key features. As a result of the missing features, a quasi-experiment does not show causation in the same way that a true experiment does. But it can sort of hint at it. It's one step above a purely correlational experiment, a purely correlational study. It's better than that. So it can sort of hint at causation, but it can't show it as decisively as a real experiment. So the first kind, which is the weakest kind, is one group post-test only design. So you have a group, you do some kind of intervention on everyone in the group, and then you measure the dependent variable. So here's the group. There's some independent variable. You give them all one level of the independent variable, and then you measure the dependent variable. So let's say you want to know if CBT reduces depression. You get 50 people, you give them all CBT, and then at the end you measure their depression. There are several things missing here. So given that there's no, so let's say at the end, their depression score, I I forget what the back depression inventory is out of, but let's say it's 4 out of 10. It's the back depression inventory is not out of 10, but just suppose that's their depression score. Okay, well, we don't know what it was before. So, did it go up? Did it go down? So this is kind of useless. So there's no measure before, and obviously no control group. Is that your? Yeah. There's no control group. No control group and no measure before.
Would there ever be a situation where somebody would use that?
I've never seen it in a study.
It just seems like
Maybe if you're really cheap. I don't know.
it just seems like you would want to use the next one.
Yeah, so the next one is one step up. It takes slightly more effort, but not all that much, which is one group pre-test, post-test design. So in this case, same idea, but you measure their depression before and after you do the intervention. Yep.
For instance, there was one they did at college campuses where they had a clown on a unicycle riding around. And then they would, like just through campus, and they would ask people as they came inside, hey, did you see the clown? Hey, did you see the clown?
Yeah.
And they would check to see whether the students were on
Good.
their cell phones or not.
Good. So that is an example. So assuming you don't measure cell phone use before, you just do the clown and then measure something. Yeah, then that's one group, and there's only a post-test measure. So, okay, there's one example.
Answer my
Nice.
question.
So not never used. As the person hints at, though, the next one is all else being equal better if you have pre-test and post-test. So as I say, in this case, you measure depression before and after the intervention. So now, even though it's better, there are still issues here, and the issues relate to something we saw in a prior chapter, which is internal validity. Internal validity is, let's add space. So your hypothesis is that the independent variable causes a change in the dependent variable. If you want to put it like this, internal validity is how confident are you in this error? How confident are you that the independent variable is what caused the change in the dependent variable? And zooming in on the one group pre-test, post-test design, there are a number of threats to internal validity. Because there's not random assignment and some other features associated with a real experiment, you don't have high internal validity. And what these threats relate, at least one thing they relate to, is the absence of a control group. So the one group pre-test, post-test design doesn't have a control group. One thing that can be going on is what the book calls history effects. So something may have happened in the intervening time, unrelated to your intervention, that caused the change. So one example the book uses is, suppose you're doing some kind of anti-smoking intervention. Maybe during the course of your intervention, let's say it's several weeks or something, maybe a famous smoker dies and it's all over the news. Maybe they did less smoking at the end for that reason. If you had a control group, the control group would also be affected by something like that. So then you're more able to make the inference that the independent variable is what made the difference. So if you don't have a control group, it could be anything like that. Another one is maturation effects. People change over time. People hopefully usually get wiser as they age. Or maybe not. Maybe people get more dumb as they get older, whatever. But there could be changes that have nothing to do with the intervention. Another one, testing effects. The act of administering a pretest may itself have effects on how people respond later. You know, there's some evidence that just the act of introspecting and paying attention to your own states can lead to you improving in various ways. So again, this is a threat to internal validity, because if it's the pretest that's having the effect, well then it's not the independent variable. Again, if you have a control group, this problem is solved because both groups are exposed to a pretest. The only difference is the independent variable. Any questions? I've rattled off a few terms.
So,
Yep, sorry.
Can you say the last term of that function again?
Yeah, so testing effect would just be administering a pretest might have an effect. At least in this context, that's what it means. Next, instrument decay. This is, oh, sorry, no, yeah.
Oh, and can you repeat history effects and maturation?
Yeah, so history effects, if you want a one-sentence definition, some event that occurs at the same time as the intervention might have an effect. Like the famous person with smoking dies. And then maturation effects have to do with just people changing over time, you know, maturing. Okay, so the next one is instrument decay. So this is more obvious in the case of physical instruments. So, I mean, this literally happened to me. I mean, I worked in an EEG lab, and the EEG machine is not made of magic. It's made by humans, and over time, it starts to suck. And so changes that occur in measured variables may be just due to the fact that the EEG machine is starting to suck. In the case of psychological scales, the book says that technically included in the term instrument decay would be, you know, people respond in a less motivated way to stuff. So the first time they do it, they answer really carefully and honestly. The next time they do it, they're kind of lazy, and maybe that leads to a change in responding. Now, if the physical device one makes more sense to you, you can stick with that example. It's definitely a more straightforward example of instrument decay.
Is there like a definition?
Yeah, so one sentence definition would just be measurement device decays over time. That's totally fine. If you want to write more fancy stuff, that's fine too. Okay, next one, and this is a really good term to know in general. This is a very well replicated finding throughout different sciences, not just psychology. And it's relevant outside of quasi-experiments as well. It's just a good thing to know, and that's regression towards the mean. So regression here does not mean regression like linear regression, like in correlational studies. It means more like going backwards, like that sense of the term. If you want one sentence, all else being equal, scores tend to move closer to the mean over time. All else being equal, scores tend to move towards the mean over time. So this is true in all sorts of contexts. One context that's widely talked about, if you are very, very tall, even if you and your partner are both very, very tall, your kid is likely to be shorter than both of you, all else being equal. Because over time, scores tend to revert back to the mean. So even with a purely physiological example, that's what you find.
question?
Yep.
Does this have to be in a certain time frame because height is increasing?
No, that's true. So over time, height is increasing. I guess one thing I'd say is where you see regression to the mean especially strong is with extreme values. So values very far from the mean. But that would be, I guess, another variable you'd have to keep in account because yes, height is going. And actually, since it's such an important concept, I'm going to show a video talking about regression to the mean. Although I guess just before that, just again going back to quasi-experiments. So if you're doing the pre-test, post-test design, if the pre-test score is already low, so maybe it's just a class, people are just starting off, they just got very unlucky on the early tests, you do some kind of intervention, well, maybe they just happen to start off really bad, and all else being equal, they'll tend to move closer to the mean. So this is another thing that could be the reason why scores change after the intervention. Okay, so nice example. Okay, so the key thing that was missing from the prior quasi-experiments and that leads to all these other things being threats to internal validity is there's no control group. That's what the prior ones don't have. So the next two, actually another one after, do have a control group. So the first one with a control group is non-equivalent control group design. So non-equivalent here basically means it's not the result of random assignment, right? The two groups are not made to be the same. So you get two groups, and maybe you try to pick two naturally occurring groups that are sort of similar, but because you haven't done random assignment, you can't rule out confounding variables. So I think when I was talking about internal validity, I gave an example. I didn't use this term, but this would be an example of a non-equivalent control group design. I try my old teaching method with students at Corpus Christi. I forget if I mentioned, but I'm teaching at a Catholic school in the fall, which is kind of funny because I'm an atheist. They didn't ask. So joke's on them. They did make me sign something like saying I won't be rude about it. So I'm like, okay, no Catholic jokes. So I try the old teaching method at Corpus Christi, so that's like the control group, and I tried the new teaching method at Douglas College the next time I teach it. And let's say, the Douglas students do better. So obviously this is review, but we can't infer from this with a lot of confidence that the new teaching method caused the better performance. Because it could be there's a difference between the Corpus Christi students and the Douglas College students. But it's at least better than what we've seen before.
Is this also what we would use, for instance, if we had two different classrooms of students, both of them in grade 2, but we don't actually get to choose which kids are in each class, and
Exactly.
therefore this is the equivalent name for that?
Yeah, exactly. So let's, unless you randomly assign kids to the two classrooms, you just take the groups as they are and do something with one class and don't do it with the other class. Yeah, that would be another example. Or, maybe you're doing a medical trial, you're trying a new drug, and you give people in hospital A the placebo and people in hospital B the new drug. So there's no random assignment, but you at least have some kind of control group that you hope is at least sort of similar to the experimental group, or the quasi-experimental group. Okay, the next one you can probably piece together what it is. Non-equivalent control group pre-test, post-test design. You add a pre-test. So, maybe I measure GPA before here. Well, that's a little bit of a different variable, so maybe that's not as good. Let's say it's the hospital case. So there's two hospitals, Hospital A, Hospital B, and I'm measuring tumor size. So I measure tumor size before and after the intervention. And if tumor size is equal, or roughly equal in the two hospitals before my intervention, okay, that's a little better. Now we have more confidence that the drug is what made the difference. But you still don't know for sure. Maybe, yeah, sure, maybe the tumors are the same size at the beginning, but maybe hospital A has more quick healing kind of people who recover faster. You still can't rule that out, but you're at least have provided some evidence for internal validity. Any questions about those two?
Yep, question.
Oh, yeah.
If the starting point is different, but like you're curious about the change, right? So if you're starting 20 points, but at the end you're 50 points apart, would you be able to say that this is like not obviously good as an experiment, but still kind of showing more of this?
Good, yeah, so good. So I was describing a case where you start off the same. That's obviously ideal, but you could also have a case where, fine, they start off different, but you can still tell this group got better, or better at a higher rate than the other group. And yeah, then that's still, as you say, not as good as an experiment, but you still have better internal validity than if you only have the one hospital.
But you still can't make a causal claim from that, right?
Well, it's a free country. You can do whatever you want. You can make it and just say, well, take this with a grain of salt. We didn't do a random assignment. Yeah.
Wouldn't, like
There's no God, like the God of science, who will send you to science
No.
hell if you say something like that.
But I mean, like, if you wanted to submit it to a journal, you couldn't write in the article, therefore, this is a causal claim, like.
No, well, you'd probably say something like what I said, like this is suggestive of causation, but blah, blah, blah.
Yeah.
And there's some cases where where random assignment just isn't feasible, and you say, this is the best we could do given practical constraints,
Yeah.
so it points in this direction, but take it with a grain of salt.
That's what I was meaning, it's like in the scientific community, they wouldn't.
Yeah, they would probably want you to say suggestive of
Okay.
causation. Okay, next, interrupted series design. So this is sort of similar. If you want to write a definition, this isn't quite right, but it's sort of like you have many pretest measures. That's what's meant by series. So I think this is the example the book gives. Yeah, so let's say you have, year after year a measure of highway fatalities. And then in 1 year you do some kind of intervention, like some kind of, seatbelt law or more cops on the road checking for speeding or whatever. So, here's the fatalities year over year. So you have year on the x-axis, and then at this time there's some kind of intervention, and highway fatalities goes down. So you still have all the concerns about history effects. Something else may have happened that year. So what someone would try to argue, you see this a lot in politics, right? So in politics, some event happens and crime goes down or crime goes up, and you try to argue that yes, this is the thing that led to the change. And look, it's better than nothing, but what you want to argue is there's nothing else relevant that happened that year, which of course you can't really know, but you kind of do your best to rule out possible confounding variables. So a similar method, control series design, sort of like the non-equivalent group thing. You have some other comparable area or group where the intervention didn't occur. So maybe Ontario does this traffic intervention, but BC, here I'll make it a different color, let's say BC is red, doesn't have the new law. Let's try green. Green, beautiful BC actually. So BC is like this, and BC doesn't have the intervention, and fatalities stay high. Okay, again, can't rule out completely that there are alternative explanations, but you have more confidence that it's the policy intervention that made the difference in Ontario. So I have a real example here from John Green. He summarizes here a famous study in economics. So one debate in economics is the extent to which increasing the minimum wage increases unemployment. So if you trust kind of standard economics models, the logic is pretty simple. If you raise the minimum wage, you thereby make labor more expensive, and all else being equal, companies will hire fewer people. So there's a kind of economic logic to that, but there are critics who doubt the extent to which that's true. So one early study looked at two neighboring cities that were very similar in terms of population and other variables, but there was a state border. I forget which states, you'll say in the video. There's a state border between these two similar cities. One state raised the minimum wage and one didn't, and then you can see what happens in the two cities. In this specific case, actually employment went up in the city where the minimum wage was increased. This is just one study. Some find the opposite effect, but it's a nice example of a control series design. So he says some more stuff at the end, but you get the idea. So that famous economic study is an example of a control series design. Okay, next, which is technically an experiment. It has experiment in the name. It's just kind of a not that good experiment, is a single case experimental design. So as the name suggests, you have one subject and you manipulate the independent variable. So you can think of it as like a within subject design with an n of 1.
Okay, there's
So-
one subject and manipulation is applied.
Yeah, exactly. So the best way to do this is some kind of reversal design where you go back and forth. Because if you just do it once, you're subject to all the issues that we've already talked about. So this time's called A, B, A, B, and you can do it as many times as you want, really. I think an example that I have a video of this. Maybe you are trying to reduce problematic behavior of someone with a kid with a developmental issue, so maybe like violent outbursts, someone who has autism. So you have the baseline number of violent incidents, and then there's an intervention, maybe some kind of token economy where they get rewarded when they behave well. And then you go back to baseline, so back to no token economy, and then back to token economy. So you do that a few times, and if it starts off with lots of bad behavior, then you do the intervention, bad behavior goes down, get rid of the token economy, bad behavior comes back. If you get something like that, again, you have more confidence that the intervention is making a difference. Okay, so that's reversal design. Again, I'll show a video. So yeah, with this example, again, just take violent outbursts of a kid. Let's say this is like how many they have. And treatment could be some kind of token economy, or it could be medication. So you give the medication or implement the reward or token system. Number of outbursts goes down. And then reversal is you go back to the baseline conditions. So no intervention anymore, and it goes back up. Reintroduce the treatment, and the DV goes down again. So if you have a case like this, that's again good evidence, albeit only with one subject, that the intervention is making a difference. And as the book says, you can do more than just 4. You can keep doing it, and then the more you have, the more confidence you'll have in effect of the intervention. Yep.
What if the intervention has long-term effects, so that even after it's removed, you don't go back to the patient?
Yeah, exactly. Like, I forget if I saw this either in the book or somewhere else. Like, let's say it was like, cognitive behavioral therapy. Well, cognitive behavioral therapy, we know with, legit experiments, does have an effect, but probably stopping the therapy won't result in going back to this. So only, as your question implies, only more short-lived interventions will give you this kind of pattern. Yeah, it's a good question. There's then multiple baseline design. Ignore that.
Cool.
It's the way they define it. It sort of could include just ordinary within subjects experiments. So just don't worry about
Ignore which one?
it. Multiple base. It's in the book. I don't think it's even in the key.
It's
No,
not.
no, no,
So there you go. Very easy to ignore. Okay, so the last section in the book is about developmental methods. So methods used by developmental psychologists. So you should have seen at least a couple of these in Intro Psych, I guess 1100. So I'm going to go in a different order than the book goes. I'll start with cross-sectional design.
Okay.
What?
Is it okay?
Oh. It is only okay, this method. So, you will have heard me use this example if you took my intro class. Suppose your hypothesis is that aging leads to people liking slower music. I think that, people's bodies and brains are slower as they get old, so as a result, they like slower music more. I have no idea if anyone studied this, perfectly fine hypothesis, but I want to test it empirically. If I do a cross-sectional method, what I will do, or use the cross-sectional method, what I'll do is I'll get a group of 20-year-olds, 30-year-olds, 40-year-olds, etc., up to whatever, 70-year-olds, and measure how much they like slow music. And let's say it turns out that the 70-year-olds like slow music more than the 20-year-olds. And I conclude, aging leads to you liking slower music.
There's so many different generational.
Good, so there's so many different generational things. That's a way of saying cohort effects. So cohort effects in this context means effects that have to do with what generation you're a part of, or what, you can put what generation you're a part of. In this context, that's fine. So, the people who are 70, it's not just that they've aged, they grew up in a totally different generation with different music tastes and other differences. So, the cross-sectional method fails to control for cohort effects.
All right, your one-sentence definition, please, sir.
For cross-sectional?
Mm.
Yeah, so a method in which you measure people at multiple ages at the same time. Exactly. So the next method, longitudinal, you get one, so the one sentence definition would be you get one group of people and measure them as they age. So you get a group of 20-year-olds, you measure how much they like slow music. You call them up to come back to the lab when they're 30 and measure them again. How much do you like slow music now? And keep doing that until they are 70.
Or until you're dead, whatever.
Or until you're dead. So the one downside is you will lose people either to attrition, like some people just don't want to do the study anymore, or some people die. And thus are unable to participate in your study. But it has the advantage that it controls for cohort effects, because it's the same people aging. Yep.
I'm struggling to understand the relation between cohort effect and cross-sectional research.
Yeah, so cross-sectional fails to control for this. This is a problem for the first method.
From your example, it seemed like cohort effect is what we're trying to find. The example I told you.
Good. So my hypothesis is that, I'm very glad you asked that. My hypothesis is that just aging, the process of aging, causes you to like slower music. But, and let's say that my prediction is confirmed, the 70-year-olds like slower music. It could be because they got older and their brains got more slow, or maybe they grew up in a different time when there was more, slow. So that's what's not being controlled for. Good question. Okay, the last one, sequential, basically just multiple longitudinal studies. So you get multiple groups and follow all of them as they age.
Okay, so multiple longitudinal studies on the same dependent variable done in tandem?
Yes. Yep.
Can you repeat that? I didn't really understand it. So
The what, sorry?
the sequential method?
Yeah, so like, now, the way the book says it is a bit more narrow than it needs to be, but one example could be, I get a group of 20-year-olds, 30-year-olds, 40-year-olds, and measure them all as they age. Or I get a group, it could be also I get a group of 20-year-olds now, follow them as they age. Then when another cohort turns 20, follow them as they age. But the point is that it's multiple generations and watching them all age.
Is the goal of it to make sure that it isn't just happening because of a specific group and how they grew up?
Exactly, like maybe one group, maybe millennials age differently than a different group. But strictly, all that you have to write, the way I would write it, that I think is the clearest, is you get multiple cohorts and watch them all age, or measure them all as they age.
And the cohorts can be of different generations.
They can be of different generations or different ages when they start. Now, so the advantages of the latter two should be pretty clear. The downside is they are a pain in the ass, right? 50 years is a long time. You gotta get lots of grant money, and someone mentioned death. The researcher retires or dies. You gotta get someone else to keep the ball rolling. As a result, studies like this are not often done. But just as an example, one of my favorite TED Talks is certainly one of, maybe the longest longitudinal study done in psych. Some kind of nice findings from it, so we'll watch that. Okay, so a very nice study. Now, one important caveat to add, so if you're watching this later, the punchline of this longitudinal study is that good relationships were the best predictors of good health and happiness in old age. Now, one thing, of course, to point out, because he does make a lot of causal claims in the video, strictly speaking, this is still correlational evidence, although at least you can establish temporal precedence. You can see which things come first, but it is still correlational, so you have to take it with a grain of salt, but it's still a cool study. Okay, let's take our break. Let's come back at 5:15. Okay, so previous chapter was mainly on quasi-experiments. This one is on advanced experiments. These are real experiments, but experiments that are more complicated than the intro psych ones that you get. So a word we have to introduce here, and I should say the bulk of the chapter is on a special kind of advanced experiment, which is a factorial experiment. Most of it is on that. But the first type, which is pretty easy to go over, is you can have an experiment with more than two levels of the independent variable. So we have to explain what a level is. So you can think of a level as how much of the independent variable do you get?
How much of the
Independent variable. So for example, the example I use in intro is, you get a group, randomly assign them to two groups. Let's say, and you're manipulating sports, so how many sports they play. The control group plays one, experimental group plays 5, and then you measure extraversion. So sports is the independent variable. So, and then extroversion is the dependent variable. So in this case, there's 2 levels of the independent variable, 1 sport and 5 sports. So level, as I say, how much of the independent variable do you get? But there's nothing stopping you from having multiple levels. I mean, you could do this. So then you have 4 levels of the independent variable. Obviously, the more levels you have, the bigger sample you want. If you want the number of people per condition to stay the same. Yep.
For instance, what if you've got a group of people, let's say you got 3 different groups of people, and they're playing, one of them's playing volleyball, one of them's playing chess, and one of them's playing a computer game. And you're assessing their levels of mental exhaustion after these games.
Good.
But these games have absolutely nothing to do with each other, and therefore, how do you assign levels?
Yeah, so the
to
independent
that?
variable there is going to be activity. So good. So in that case, it won't make sense to say how much of the independent
Yes.
variable, because it's more of a nominal
Yes.
one. It's not a quantitative one. So good. So in a case like that, speaking of them as, the operationalization of the independent variable is going to make more sense. So I guess a more broad way to say it is operationalization of the independent variable. How do you operationally define it? So in this case, it's the number of sports they are told to play. In your case, it's going to be which activity they are told to play. It's not, you're not going to be able to have a number with each one.
Yeah, no, I'm just trying to figure out how to do a 1-sentence definition.
Here's what I'll say:
that
the
makes
one I
sense.
gave is fine if you want to say how much of. If you want a broader one, you could say how the independent variable is operationalized, or how it's operationally defined in each group.
In each group.
Yep.
With an experiment that has an experimental condition, a placebo condition, and a full control nothing condition, would that be considered also like a multiple level experiment? Because,
Yeah.
like, there's only technically one experimental path.
Good. So it just has to have more than 2 conditions to
Anything
fall.
more-
Yeah, anything with more than 2 conditions is going to fall in this category.
So it has to have 3 or more?
3 or more. Yeah.
Sorry, I just learned about ANOVA tests today, and I'm like, oh boy,
There you go.
oh
So yeah.
boy.
So we
Overlap.
don't talk about ANOVAs in this class. Although yes, for the methods we'll be talking about, ANOVA is what you'll typically use. If it's just 2 groups where there's random assignment, you use a t-test. If there's 3 or more, you'll typically use ANOVA. There's also ANCOVA and other stuff, but
Yay.
none of that we have to worry about in this class. So why would we do more than 2? One concrete reason is it would allow us to uncover a curvilinear relationship. So, think back to my example from an earlier chapter, the relationship between masculinization of the face and attractiveness. So if you're doing random assignment, like an experiment, you will, show people different faces with different amounts of masculinization. So that's the independent variable. And then you measure, their response to the question, how attractive is this face? If you only have 2, and so the relationship in fact is something like this. This part is a bit higher, but it curves. If you want to do this experimentally, you need at least 3 levels, right? You can't just have 2. So you wouldn't get all that detail, but if you're doing an experiment, you want the means to be something like that. That would be. So you have to do that if you want to uncover a curvilinear relationship.
And that's the levels.
Yeah, you need 3 levels. Okay, so that's more brief. As I say, most of the chapter is on factorial experiments. Factorial experiments involve the manipulation of more than one independent variable. So in the standard intro psych example, there's one independent variable with two conditions. As we just saw, you can add more conditions if you like. A factorial experiment means you have more than one independent variable. So let's spell this out with a really concrete example. Let's say I have the following hypothesis. I think that caffeine affects mood, but the effect that caffeine has on mood is different depending on how hot the room is that people are in. I don't know of any studies on this, I'm just kind of making this up, but let's say this is my hypothesis. So I think, well, actually, before I say what I spell this out, if I want to test that hypothesis experimentally, I have to manipulate two independent variables: caffeine level and room temperature. So let's say we just have two levels, or two groups, or two operationalizations for each independent variable. Then we'll have four groups. You have to randomly assign people to the four total conditions. So we have caffeine, high and low. So people in the low caffeine get decaf, or maybe like tea or something, whatever. I guess making coffee is better because they're holding fast other things. So you have decaf coffee and normal coffee. And then room temperature, also you have low and high. So put people in a cold room and a hot room randomly. So let's say this is my hypothesis. I think that if it's a cold room, caffeine will make people happier. You know, they feel cold, it's unpleasant. Caffeine gives them some extra juice and allows them to persevere through the cold. As a result, they feel happier. But in the, I'm just going to change this to make it consistent with the graphs that are drawn right here. Put high here and low here. So I was saying, in the hot room, the extra caffeine will make them feel unpleasant. It's already hot, you make it jittery, and it makes them kind of irritated and feel less pleasant. So without adding numbers yet, basically I'm predicting this. So the cold room, so ignoring this, within the cold room, caffeine will make people happier. But within the hot room, caffeine will make people less happy. So that's what I'm predicting. And again, random assignment does what we want it to do. If we have a big enough sample and randomly assign people to the four conditions, we can assume they are roughly the same in terms of mood at the beginning, and any differences at the end are due to, in this case, the two independent variables. So how are we doing so far? Does the basic logic make sense? Okay, let's add some numbers. This will help us, will help me explain the different terms. So let's say it looks like this. So let's say my hypothesis is right. So we ask everyone how happy they are on a scale of 1 to 10. We get an average of 7 in this. Oh, and I should say, the term for these are cells. So that when you put this in a chart, you have the cells. So in this cell, it's 7. 3 here. So then what you can do is add something called the marginal mean. So the marginal mean is the mean for this whole, for everyone in the hot room in this case. And we'll assume equal sample size in each cell, so it'll be 5. And then for this one, we'll say it's 2 and 6. So then the marginal mean will be 4. And then And again, if we're assuming equal samples, it'll be 4.5 here and 4.5 here, assuming I did the math right when I prepared this. So there's some made up data. Let's add some more terms. So one important term here is main effect. Main effect is the effect of one independent variable ignoring the other one. So let's say, for example, we're looking at room temperature. The main effect is going to be the difference between these two marginal means. So we're saying, let's collapse across the caffeine conditions and just look at what the average effect of room temperature is. So in this case, being in the hot room makes you slightly happier if we ignore caffeine. I don't know if it's significant with this made up data, but that would be a small main effect. Yep?
Is it always main effect of X independent variable? And
Yes. So it's the effect of one of the independent variables on the dependent variable, but you're ignoring the other independent
so it's not like the main effect of this step. It's the main effect of this independent variable, and the main effect of that.
Exactly. Yeah, main is kind of misleading. It doesn't mean important or, you know, it just means the effect of one independent. I'm not sure why it's called main, but for whatever reason, it's the effect of one independent variable ignoring the other one. So caffeine, there is no main effect in this case. 4.5 in each. Now, when you look at this, you should sort of get the sense that the main effects aren't what matters here. Where all the action is in what we call an interaction effect. The dash is just because I ran out of room. It's one word, interaction. There are different ways of stating this. The way the book states it, the effect of one independent variable depends on the other independent variable. The effect of one independent variable depends on the other independent variable. You can state it this way, it's the same meaning. The effect of one independent variable is different depending on the other independent variable. So what that means is, if we want to know about the effect of caffeine, someone comes up to me and says, so based on your study, what is the effect of caffeine on mood? The answer is, it depends. Is the person in a hot room or a cold room? If they're in a hot room, caffeine makes them less happy. If they're in a cold room, caffeine makes them more happy. So that's an interaction effect. As I say, the effect of one independent variable is different depending on the other one. Yep?
If we were doing a study on the effect of caffeine on mood, would the temperature of the room then be like a confounding variable? Because if we did it in a hot room, it would look that. If we did it in a cold room, it would look that. But if we're doing the study, we don't know that because we're not thinking about the temperature.
It wouldn't be a confounding variable. The fancy term for that will be it's a moderating variable. And in a case like that, it's a hidden moderator. So just as an aside, so we've talked about the replication crisis. I think I used the word cope at one point in that lecture. So cope is like when you make something up to make yourself feel better, also known as copium. So what often happens is, so Bob does a study, Bill does it somewhere else and can't replicate it. What Bob, the original guy, will say is, well, maybe there's a hidden moderator. So it is a real effect, but it only happens in these conditions, and you didn't have the right hidden conditions, which I don't know what they are. So it's very convenient, a very convenient form of copium. Which is not to say that it isn't sometimes true, but if you keep saying that after many failed replications, people should start to look at you with, suspicion.
The squinty eyes.
The squinty eyes is the right response to people always say hidden moderators. So this is a very important term, nudge nudge. Any questions about what an interaction is?
Is it similar to a correlation?
No. So this is an effect. This is an effect that you've discovered through the experimental method. And it's one that you can't get if you only have one independent variable. Yep.
Is it like saying the effect both independent variables have together on a dependent variable? Or is that
Yes, you could say it like that. Yeah. So the two independent variables have an effect on the dependent variable together, and it's not in a simple you just add the effects together. There's something special that happens when you put these two together. So for example, if let's say that caffeine gives you 1 point of happiness, all else being equal, and a hot room gives you 1 point, you have both and then you have 2 points, that's not an interaction. That they're just adding them together. It has to be the effect of the independent variable changes when the other independent variable is manipulated.
So how is that not correlation?
Well, this is causal. Interaction effect is causal.
Okay.
But you could still map it like correlation or.
Yes, well, you can always map causation correlation.
Yeah.
You can represent it as a relationship.
I think that's what she was asking. Was like you could map
Sure,
it.
yeah. So in that broad
Well, no,
sense,
it's
yeah.
just that's the definition of correlation is that when the independent, that the two things change in the presence of each other.
Well, change in the presence of each other, but this is causal. That's the key thing I want to make sure isn't missed out. An interaction effect is causal. Yep.
Except what you're talking about there is talking about one thing is correlated with another thing. Like, room temperature is not correlated with levels of caffeine. If you change the room temperature, the amount of caffeine in a person doesn't change. But if the amount of caffeine combined with the temperature of the room are different, you will get a different result.
Good.
Yeah.
Yeah. So that's another good thing to add. So yes, given that it's an experiment and there's random assignment, room temperature and caffeine will not be correlated. Yep.
Assuming your numbers are statistically significant, would there be a interaction effect on that board? Like the
Oh,
five-
for sure. I mean, if there's any big sample, this would be quite a big interaction effect. Yeah. And also, well, I'll add something more in a second, but this is kind of a special kind of interaction, and it's rarely quite this beautiful, for reasons that I'll add in a second. But there was another hand.
What if instead of a 3, it was a 7? So you have
This one?
Yeah.
Yep.
So in like one case you do have an interaction, in one case you don't have an interaction, but it's not like it's opposite. So it's
That
not
would
you're
still
adding
be an interaction.
That would still be.
Yeah, so, and actually here, since you've asked that, I'll go ahead and draw what I was about to draw next, but there's another hand.
I was just gonna ask the final definition for this.
Yeah, so the 1 sense definition, and this is the way I would put it, the effect of one independent variable is different depending on the other independent variable.
Thank you.
Yeah. Okay, so this may help some of you. I'm gonna draw this data, the same data, but with a different way of representing it. So this may help some of you. So this is mathematically equivalent, but it's a different way of showing it. So we'll make this happiness. We'll make it 2, 3,
Yeah.
7.
Yeah. So that's what this.
So we have 2 conditions.
This is the way my brain is defining it.
Low
It works.
caffeine or decaf, high caffeine. Now here's the fun part. I don't have it drawn, I just have instructions to myself. We'll have 2 lines, one for the hot room and one for the cold room. So we'll make the cold room blue and the hot room green. I would have made it red, but red died. So cold room is
Alright,
blue. Cold room blue starts at 2 and then goes to 6. And then hot room, which we'll make goes from 7 to 3. So then so we have two lines here. This, the green line corresponds to the hot room, the blue line corresponds to the cold room, and then here we have high caffeine and low caffeine. So one way to say it is the difference between this and this different for the two lines? And in this case, it's completely different. In fact, it's the opposite direction. So this is a case where the interaction effect is on the direction of the effect. Is it positive or negative? You can also have cases where the interaction is not on the direction of the effect, but the strength of the effect. So let's imagine a different case. Well, actually, first I'll just show a case of no interaction. Let's say it looks like this. Basically, if the lines are parallel, in this case, all you have is two main effects. There's the main effect of caffeine, right? Which is positive, and there's the main effect of the room, which is the gap between the two lines. But given that the lines are parallel, there's no interaction. Let's say it's something like this. So this is still an interaction. But here, it's not the direction of the effect that changes, but the strength. The effect of the room is larger in the high caffeine condition than it is in the low caffeine condition. So that would also count. And this is more often what you'll see. A full-on one like this, where the effect is the opposite, that's pretty rare. Though it's cool when you find it. So just to hammer this point home, I have a video of someone else giving some other examples of interaction effects. Okay. So this is a difficult concept when you're first exposed to it. Any other questions about interaction effects? Yep.
I don't have a question. I have an example that's helping me
Sure.
with this, and I just kind of wanted to throw it out to the class. The synergistic one was very much like what you were talking about, which is if you take one, it magnifies the effect of the other.
Good, so that definitely is. So if you take two drugs, and actually, there's literally a term, synergistic
Yes,
interaction.
synergistic.
So synergistic interaction is where taking the two together, like this. So the high caffeine, and in this case the colder is making you happier. That's kind of weird, but let's just say it turns out that way. Caffeine and room temperature together have like a bonus effect. So that would be, yes, what's called a synergistic interaction.
And then the other one, the antagonistic, which is also an interaction,
Yes.
which is like with cocaine and alcohol, where if you take cocaine after taking alcohol, you will no longer be as affected by the alcohol because it stops
Right.
the liver from metabolizing it.
Good. So yes, that is a good example. So if drugs or if that really makes it concrete for you, there you go.
It's just an example.
Merry Christmas. Okay, so a couple other terms here to know. Moderator variable. So you could basically put in brackets interaction variable. It just means a variable that affects the relationship between an independent variable and a dependent variable.
Between
So,
an independent variable.
So well, the one sentence is it's a variable that affects the relationship between an independent variable and a dependent variable. So in the caffeine and room temperature case, you could say room temp. And which one you call the moderator variable is really a matter of choice if you are manipulating both. So we could say the room temperature is a moderating variable or moderator variable, meaning it changes the relationship between caffeine and mood.
But it can also be an unknown variable as per your example.
Yes, could be unknown. Yep.
Did we go over marginal mean?
Yeah, marginal mean is the mean at the edge. So like,
The
It's
average
the-
score of everyone in a particular condition.
Okay.
or well, yes. So it's yeah. So the average score of everyone in, for example, the high temperature condition, like averaging across the two caffeine conditions,
Or
or the other.
or down way.
Yes.
Yeah.
Okay.
Row or
Yeah.
Got
So
it.
the means at the edge or bottom
Okay.
of the thingy. Yeah.
In the margin.
In the margin. There you go.
What did you
It's good to
say?
make connections. Yes, in the margin.
Thank you.
So a moderator variable could also be one that we are experimenting on and is an IB in the study, and also
Yes.
could be something that's just not in the study at all. and
Yes,
it's
or at least not measured.
It's
Yeah.
not measured. Okay,
Yeah.
so regardless of its measured or not, it's still considered a moderator.
Yes. Yeah. Good caveat, or good clarification.
Question.
Yep.
When researchers say they're doing a moderator analysis, does that mean that they're like looking specifically at that moderator's effect, or are they removing the moderator, so to speak?
Well, that's a good question. So no, moderator analysis basically means you're looking for an interaction.
Did I
Um,
miss some?
Yeah, cell is just like the
Can we
like
draw it?
the what?
On the test, can we just draw it?
In Excel,
Yes.
a single
Yeah, so actually, in
box.
general, whenever I see drawings, I like drawings when I see those on the. Yeah, so if you just point to and say, this part or whatever, that's fine.
Sounds
A
good.
single box of data?
Yeah, that's fine. Yeah.
Alright,
No,
about the
never be
moderator
sorry.
variable again. If I'm doing a study where the moderator isn't changing, I'm only doing a study in cold rooms, would I still consider it a moderating variable? Because in theory, a different study could be done in a hot room.
Yeah, so then it's a hidden moderator. So this is what I talked about earlier with the copium.
Okay.
Although signs of the copium is right. Like
It's still considered.
yeah, it would be a hidden moderator. It's one that you didn't measure, so you can't know, but it's a nice excuse when your study doesn't replicate.
Right.
Or like, if you're studying two independent variables, like you were showing, and you find out that one is a moderator, it's like, oh, hey, look, I found a moderating interaction. Like, you find it by mistake.
Like in this case, like
Yeah. Like,
I would have.
Oh yeah, you could find out like maybe I wasn't predicting an interaction. I just happened to have I mean, usually you do a factorial design because you're at least open to the possibility there's an interaction. If you don't think there's an interaction, it's kind of
how do you tell which one is a moderator of the other one?
it's just a matter of choice.
Oh, so they can moderate each other then.
Almost, yeah, by definition they will. Like you could just as easily call caffeine the moderator.
Okay.
It's just a matter of, I guess, which variable you're more interested in. The one you're less interested in is the one you call the moderator. Yeah.
So what's the difference between a moderator and
Good. So, at least in the factorial design, the moderating variable is not a confound because it's not something else that's different between the two conditions. Like, I'm trying to think how to say this.
Words are
Caffeine, I'll just draw it out. So like, so let's say I really care about caffeine. Let's say I just look at these two. I only care about caffeine. Well, the number of people in like high temp and low temp is roughly the same. So it's not something that's different. A confounding variable in the context of an experiment is something that's different between these two conditions other than caffeine. So like if there's a bunch of happy people in the high caffeine conditions, that's a confounding variable because it's something that's different between these two groups other than caffeine. But this isn't. It's controlled for, right? Because there's an roughly equal number of people in the high temperature and the low temperature conditions.
You know what it is.
And I know. Yeah. So that's my best attempt at answering that. If that doesn't help, just memorize the definition for each separately. And just trust me, bro, they're not the same.
Opium, trust me, bro.
Yeah.
Gotta love the memes.
Well, do you have a follow-up about what either one means, or is that sufficient?
I still can't tell the difference.
Good. So all I can do that, maybe I'll just try and define each separately, and maybe that'll help. So a moderating variable is something that influences. Actually, I'll do a totally different way of. So here's one way of doing it. You have the independent variable, and it affects the dependent variable. So we'll stick with caffeine. So the independent variable is caffeine. The dependent variable is mood. So caffeine affects mood. A moderator does this. It changes how caffeine affects mood. So in this case, maybe temperature. So if the room is hot, it makes, what should I say? It makes caffeine lead to lower moods. If it's cold, it makes caffeine lead to higher moods. So it's affecting the relationship between the two variables. So that's a moderator. Yep.
So I guess that's what you're saying. Switch the temperature and the caffeine.
The caffeine has if you change the temperature, the caffeine has a different effect on mood.
I see. So
Now-
those are like the graphs that
Exactly like this. Like that means a moderated relationship. A confounding variable would mean there's something that, so there's none of this business. It just means there's something that prevents us from knowing if this affects this. So for example, there's two groups. One has high caffeine, one has low caffeine. But the high caffeine group has more happy people, or more whatever. And then so the having more happy people would be a confounding variable. I see nods. I like the nods. It's a good question though. It's always good to clarify. So let's say you find an interaction effect. What you will then do is zoom in and find and look at these simple main effects. I used to mix these up a lot as an undergrad. Let's go back to.
What's your one sentence definition?
I'll give it once I get the example.
Okay.
So. Low, high, caffeine, temperature, high, low. Okay, so you looked, well actually I'll add the, okay, so these on the edge or on the margin are the marginal means. If you're looking at a main effect, you're comparing marginal means. So if you're looking for a main effect of temperature, you're saying, who gives a shit about caffeine? Just look at the difference between the hot room and the cold room. In this case, there's a small difference. Main effect of caffeine, forget about temperature, just look at the marginal mean for the high caffeine and the low caffeine. Then you look here to see if there's an interaction, and there's a very clear interaction. The effect of one independent variable is different depending on the other one. Okay, yay, there's an interaction. The next step is simple main effects, where you compare not marginal means, but cell means. So if you want, this will help you, because I used to mix these up. For simple, think zoomed in. Just make that association in your head. Simple main effect is like zoomed in main effect.
So, but it's still for only one independent.
Yes. So the one sentence definition that's closer to what the book says is you're looking at the effect of one independent variable at one level of the other independent variable.
Okay, and that's only when there's an interaction?
Yeah, you can look at them if you want, but typically you only look at the simple main effects when there is an interaction.
Okay, typically only look at when there's an interaction, and then
So would you
it's.
say like avoid the marginal mean? Like you're not.
Yeah, you're ignoring the marginal
So
means.
this-
So
So like the simple main effect would be between like 7 and 3.
exactly. So like, so we're gonna look at the effect of caffeine, high versus low, just here. So within the hot room condition, so just one that's within one level or at one level of one independent variable, we look at the effect of the other one. So does high caffeine make you sadder in hot rooms? Does caffeine make you sadder in hot rooms would be looking for a simple main effect. Whereas does caffeine make you sadder in general, collapsing across rooms, that would be a main effect of caffeine. Yep.
So you have 2 main effects in this kind of experiment and 4 simple main effects, because you can always compare.
Yes. Yeah, exactly. So in one like this, there's 2 main effects and 4 simple main effects.
Yeah, this one better not be on the test. Because
I actually don't remember. Well, actually, since I am such a benevolent teacher, there is a written question about factorial experiments.
Sorry, how are the 2, this is a tough question, but like there are 4 marginal numbers.
Yep.
How are there only 2?
Well, because to get a marginal or a main effect, you're comparing them. Yeah.
So, if you had this on a graph, would this be essentially circling a single point of information and checking what the numbers are of that?
Circling one line.
Oh, that is just not jiving in my brain.
So if it doesn't jive with your brain, just think about comparing 2 cells, not comparing 2 marginal means. So like comparing this and this. So you could do a t-test if you want. So is 3 significantly lower than 7?
So this would be, once you know that there is an effect,
There's an interaction.
this would essentially be the checking for Cohen's D.
No, you can if you want, but it's looking for statistical significance.
This is still looking for statistical
Yes.
significance.
You don't have to know that, but if you want to know what you'd be doing, yes. So what we did before is we looked for an overall interaction. And that's looking at everything here. So you get that's the interaction. And then, okay, so you want to do it like this, you're zooming in on one line. Is this higher than this? And then you do the same for the other line. So is that helpful?
That's clicking for me. I don't know for
Here, so I'll try just to do it quickly. So, you could have an interaction like this or one like this. So, that's bad for me. So, is there an interaction? You're just asking, is the effect of one independent variable different depending on the other one? So, and then you find that yes, there is an interaction, and you will get a p-value associated with that. So let's say the p-value for the interaction is less than 0.05. Okay, now I want to investigate a little bit. So I want to zoom in and say, for example, is this point on the green line significantly higher than this point on the green line? That would be a simple main effect. So I heard there was an, I'll do one more question, then I will move on because we only have 15 minutes left, and I do want to finish the other terms. Yep.
I just have a sentence that I think it makes sense
Sure.
for. Please
Yep.
tell me if I'm wrong. That looking for a simple main effect, you're essentially looking for an effect of one independent variable on the dependent variable
Yep.
in one level of the other independent
Yes.
variable.
Yes, that's exactly right.
Okay.
I will recommend this. So, given some of the questions, this is a good thing to sit down with. It's worth sitting with and spending some time with, maybe rewatching later as well. Okay, so let's keep moving just to make sure we finish everything, although we're close to the end. So one type of factorial design you can do is what the book calls an IV times PV design. So you have one independent variable that's manipulated, so it's like a normal independent variable. But the other one is a participant variable. In other words, it's one that's not manipulated. So you have the IV, so you have the experimental condition and the control condition, say, you randomly assign people. And then the participant variable is something that's not manipulated. So in my honors thesis, when I went to Douglas, I did something like this, where the participant variable was, were you born in a Western country or not? So can't randomly assign that, so there's going to be the Western and non-Western groups, but they just report that, you know, and then on that basis, I will equally randomly assign them to different conditions within the experimental independent variable. So you'll still get 4 conditions, but one of them is not experimentally manipulated. Okay, so we're almost done. The only other caveats I have to add, in the standard case, and for the written, you should just use this case. In the standard case of a factorial design, so think back to the caffeine and room temperature case, you have 2 independent variables and you do between subjects for the whole thing. You randomly assign people to each of the 4 conditions. You can have, mix it up though. You can have, for example, one of them be between subjects and one be within subjects. That is allowed. So one study I did when I was at Georgia did this. Now it actually had a 3rd independent variable, but I'll ignore that because it'll give you more of a headache than you need. So one of the independent variables was suffering, high or low. So we would describe to them a person who committed a crime and then say they suffered in prison or didn't suffer much. So suffering can be high or low. And that was between subjects. So people are randomly assigned to that. But within subjects, this one was within, we did serious crime and not serious crime. So they got to read 2 cases. So this one is within, this one's between. Now, all I'll say is, if you do this, it's a pain in the ass to analyze the data in SPSS. We had to ask a statistician for help. So that's my only warning vis-a-vis that. So that's one, the term is mixed factorial design. So mixed factorial means at least one of the IVs is between subjects, and at least one is within subjects.
If they're both within subjects, it's considered
It's just another type of factorial, but there's not I guess you call it just a factorial design using within subjects. Although, as I say, typically they're, at least in my experience, typically they're just all between. That's kind of the easiest way to do it.
So, sorry, can you repeat the one sentence?
For mixed? Yeah, so just a factorial experiment that has both a between subjects manipulation and a within subjects manipulation. And then the only other thing I have to say, we've been sticking with ones with 2 levels per condition. Look, you can have as many as you want. You could have 4 by 8, 16 by 3, and you can have as many independent variables as you want to. You can have 4 by 3 by 7, and then you have to represent it as a cube, I guess. Obviously, the more you do, the bigger sample you need. It can get pretty crazy, right? If you have.
just do everything within subjects and you're fine.
I guess there's that, right? That's true. Then you'll just have tired participants.
Very tired.
You're gonna have annoyed participants by
Yes.
the end of it.
Okay,
Nice,
so that's all I have to say. So reminder, next week your paper is due. So it's due 3:29 p.m., 1 minute before class. Please upload it to Blackboard on time, and bring a physical copy to class. So you have to do both those things. And then that week, of course, will be our last lecture. So I'll stick around if you have extra questions. See you all. Are the questions related to the paper?
Yeah, I was just asking for doing anything with paper or just giving you the.
You just give me the paper. Yeah.
Is the final cumulative or is it just on?
The final is not cumulative. It's just on 4. I was 2 lectures, 4 chapters.
And so you want us to print out the paper?
Print out the paper, double-sided, please.
Okay.
Is there any?
Double-sided?
Is there what?
I don't.
Here.
I don't know. I don't. Maybe. I don't know what that is. Just use the library. That's like. Yeah.
Is it okay if my printer doesn't print double-sided?
Same. It literally like shits itself if I try to do double sided.
Yeah.
I'll say try to do it in the library. If
The GSU will allow 60
You
pages.
go
It's less
to
money.
the students' union, at
Yeah.
the front desk students' union, you get a certain number of pages
Like
every
50 pages
semester for free.
okay, so you have a few options. I'll say, look, if you give me something single-sided, I won't. It's one of those things where I won't take marks off, but I'll be crankier when I mark your paper. So
Why do you prefer double-sided?
There's probably
I just- yeah, there could be. I like just flip it. I find I read it quickly and more visually. It's just more pleasant.
Because I've had,
Also, you're saving the earth. That's not
Yeah.
good. But the real reason is I find it more pleasant.
I had a professor threaten me with death if I gave him the double-sided.
Oh, okay. No, I will not do death either way. I don't believe in.
No, he's an ethical psychologist.
That's right.
No moral.
No joke. I had a prof once who said, "I'm bringing back your papers on Wednesday, and I'll bring a handgun if anyone wants to shoot themselves." He was